everyone, welcome to the course on medical biomaterials. We will continue on this topic of metals. In the previous class I was talking about crystal structure, okay, different classes of crystals and the Bravais lattices, and before that I talked about Miller index and how to calculate a Miller index of a plane. Okay. So, I did mention there are 7 crystal classes: cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic and trigonal, and in each of the class you can have a primitive structure, you can have a body centered cubic, face centered cubic or side centered. So, there are 14 Bravais lattices. Okay. All the metals, even salts for example, will fall into this if they are crystalline in nature. Okay. So, crystallinity determines some of their physicochemical properties. If you are interested in preparing metal alloys, what type of metal to add to existing metal to change its properties, if we know in which crystal class it will fall and what based on the dimension of the element, we can decide what type of new crystal class it will fall into. So, understanding the crystal structure is very important. We have powder X-ray crystallography, which can help us to find out the crystal structure of various materials, organic molecules, inorganic molecules and so on. Okay. So, trying to understand this is very important. Like I said, it determines the physicochemical properties. These crystal structures can change as a function of time. Okay. It can change depending upon the presence of impurities and so on. Okay. So, if you take for example sodium chloride, okay, sodium chloride forms a nice crystal. So, like I said, this is the unit cell, that is the repeating unit, keeps on happening. Okay. So, we can have this like a chlorine atom, this is a sodium atom. So, NaCl. So, for every sodium there will be a chlorine. So, they are nicely beautifully packed like this because their valency is also 1. So, they all nicely packed alternatingly. Okay. So, if we take one unit cell, as you can see, okay, there are some sodiums present, but not the whole. As you can see, this particular sodium is available for this unit cell, this unit cell, this unit cell, this unit cell, and again 4 on top. So, basically this is only, okay, 1 2 3 4 8. Okay. So, only 1/8 is available for this particular unit cell. You understand? Similarly, same thing goes for your chlorine also. Okay. So, one interesting thing is the anisotropy of crystals. For example, let us take this particular crystal. Okay. What is this particular crystal? So, it has got in the corners 1 2 3 4 5 6 7 8, and also it has got 1 2 3 4 5 6 in their faces. Okay. So, that is called face centered cubic. Now, depending upon the direction, the atoms, number of atoms can change. What does that mean? Okay. What does that mean? Young's modulus of this is a copper, okay, it forms a face centered cubic. Suppose the direction is like this. So, these type of atoms are going to be, that means direction of the force or load is in this direction. These atoms are undergoing that particular force or tensile strength or tensile force or compressive force, then the Young's modulus is 66.7 gigapascal. Okay. Now, if it is the force is in this direction, as you can see, not only these two corner atoms, but also this particular atom is also part of this pull. So, the Young's modulus increases to 130 gigapascal. See, if it is in this direction it is 66.7, if it is in this direction it is 130.3, that is a big difference. Whereas, if it is in the another direction like this, okay, it goes to 191, that is the longer diagonal, it is 191.1 gigapascal, okay, lot of difference. So, if it is along the side or if it is along the face or if it is along the longer diagonal, okay. So, the Young's modulus can change dramatically, okay. So, if the direction of the force for the tension and the way the crystal is oriented of copper, for example, we may have to consider different types of numbers for the Young's modulus, okay. So, if we think calculate everything based on this, whereas if it is oriented in this, then we are in big trouble, because the Young's modulus comes down by almost a factor of 3, okay, which is a big change, okay. So, that is very, very important. Look at this. So, suppose if the plane is like this, okay, or it is like this, the number of atoms of the particular material or metal that is in contact is changing dramatically. If it is like this, only the corner atoms face the particular load, whereas if it is like this, it is not only corner, also the atoms on the faces also face it, okay. So, there is going to be a lot of difference in their yield strength or the Young's modulus, okay. So, you need to keep that in mind. So, different crystallographic planes have different atomic density, or the number of atoms in that particular unit cell will be going to different. So, obviously hence different properties, okay, the properties can dramatically change, okay. So, you need to keep that point in mind, okay. Silicon, for example, okay, this is an example of a silicon wafer. So, when they undergo load, if it is along this plane as against along the longer diagonal, the Young's modulus are going to be very different, and that is called the anisotropy of crystals, okay. And that is another point. The other point is whether the crystal unit cell is a BCC or FCC or HCP or primitive, that also determines its mechanical properties. For example, BCCs are ductile, plastic, so it is more workable. FCC ductile, plastic, but okay, little bit workable, but if you take a hexagonal, it lacks plasticity. So, it is not possible for you to work on that. So, ideally a BCC, it is very, very ductile and plastic, so we can nicely work on it and get in nice shapes of different shapes, okay. Whereas FCC is slightly more difficult and HCP, it is practically impossible to work on it, okay. So, let us go back, take an iron, it has got a BCC structure, okay. So, each of these corners, okay, and one in the middle here. So, it has a BCC structure at room temperature with an atomic radius of 1.24 angstroms. Calculate its density, its atomic weight is 55.85 gram per mole. So, if you take one unit cell, we need to know how many atoms are there. Can you tell how many atoms are there? So, this atom which inside the body center is fully available for the unit cell, whereas these corner atoms are not available because it is shared by 8 unit cells, okay. Okay. So, obviously only if there are, although there are 8 atoms, each one is shared by 8, so it is 8 divided by 8, so there will be only 1, so there will be 2 atoms available for one unit cell, okay. Okay, let us look at it more in detail. So, this is the central atom, so it has got a radius of 2r. If you take the long diagonal, let us take the long diagonal, this is the central atom, okay, and then these are the corner atoms. So, we have r. So, the long diagonal will be equal to 4r, and suppose A is the side of the cube, okay, and the long diagonal is 4r, where r is the radius of each of these atoms, okay. And like you must have studied in your school, the long diagonal is square root of 3 into side, just like in a square the diagonal is square root of 2 into side, for a cube long diagonal is square root of 3 into side. So, you must have studied this, right. So, side is a, so obviously 4r is equal to square root of 3a. So, there is a relation we can develop between r and a. Okay. So, 4r is equal to 4r, the r plus r, 2r plus r, that is 4r is equal to square root of 3a. So, a is equal to 4r divided by square root of 3. Now, volume of one unit cell, okay, is equal to 4 into r is 1.24 angstrom. So, we convert it into centimeter, 10 power minus 8 cube. A into A into A is the volume, and that is so many, that is this, okay, because r is given here 1.24, 4 into 1.24 into 10 power minus 8 whole thing q raised to the power 3. So, this is volume of one cell. Okay. Now, we need to know the mass. Now, number of atoms, like I said, one central atom plus 1 by 8 of 8 corners, so 2. Avogadro number is 6.023 into 10 power 23 atoms per gram mole. So, 2 atoms you have, the atomic weight is given as 55.85 gram per mole. So, 55.85 gram per mole, okay. Then you have the 6.023 and atoms are there per gram mole. So, we need to divide that. Do you understand? 2 atoms per unit cell multiply by 55.85 gram, but in 1 gram mole there are 6.023 10 power 23. So, you need to divide that. So, the weight is 1.85 into 10 power minus 22. So, density is weight by volume. So, 1.85 into 10 power minus 22 and volume is 2.34 10 power minus 23 divide. So, we will end up with 7.89 grams per cc, and this sort of matches with the literature value also. So, what do? We know how many atoms will be there in one unit cell, okay, 2, and then multiply by the weight of each one of them, that is atomic weight 55. We need to divide by Avogadro number because it tells you how many atoms per gram mole. Now, if you want to go look at the volume, use geometry here. If you take the long diagonal, there is one central atom and then 2 atoms placed on the corners. So, that central diagonal will be 2r plus r plus r 4r, and in our school we must have studied for a cube the long diagonal is square root of 3 into side, that is a. So, 4r is equal to square root of 3a. So, the volume of one cell is a into a into a, which is 4r divided by square root of 3 raised to the power 3, and then of course, we need to convert angstrom into centimeter. So, that is why we have this 10 power minus 8. So, we end up with 7.89 grams per cc, okay, quite straightforward. Okay. Now, there is some other term which is called the coordination number, that is the total number of neighbors of a central atom in a molecule or ion. So, obviously, suppose we take this chap, there are 3 atoms, okay, in a triangular, coordination number is 3. Suppose this is a tetragon. So, there is one like your sp3 type, 1 2 3 4 in the center. So, we have 4 tetragon. So, if you have like this hexagonal, okay, that is 6, 1 2 3 4 5 6. If you take a cube, 1 2 3 4 5 6 7 8, BCC, this is 8. If you take a FCC, so apart from okay, there are 12, 8, okay. So, there are 12 for this, that is called the coordination number. There is a number of atoms which are neighbors to this central atom, this is the black one. So, coordination number for BCC is 8, like I showed you here, okay. In diamond, for example, each carbon atom is at the center of a regular tetrahedron. So, coordination number is 4. So, we have diamond like here, diamond like structure here. So, 4. Graphite is a 2-dimensional structure, okay. So, graphite, so the coordination number will be 3. So, you will be having layers and layers of graphite, whereas diamond will be a 3-dimensional like this, a tetrahedron, so coordination number is 4. Graphite, so same carbons, but you can see that coordination number changes depending upon their structural. Graphite is made up of 2 dimension, diamond is made up of 3-dimensional regular tetrahedron. Okay. So coordination number for graphite is 3, coordination number diamond for 4. Alpha aluminum has a regular cubic closed packed structure FCC, okay, sorry, alpha FCC, so the coordination number is 12. So coordination number for BCC is 8, yeah, coordination number diamond, like I said regular tetrahedron, so it is 4. Graphite is got layer by layer, 2-dimension layer, so see coordination number is 3. Okay. Now there is a slight difference in coordination number depending upon whether it is a bulk coordination number of a given atom, that is the total, or it is a surface coordination number, that is surface means on the surface like of say cube. So generally surface coordination number will be less than the bulk coordination number. So when we say surface, we look at the surface atoms and see for a central atom what are the nearest neighbors, whereas when we say bulk coordination number, we look at the central atom in a bulk 3 dimension and see what are the atoms that are surrounding it. Okay. So if you take BCC, bulk coordination number is 8, okay, whereas if you take the surface coordination of that for the 100 plane, that will be 4, okay, because look at this, there are 4 atoms, this one which is in the middle does not come into the picture. Okay. So for a BCC, the bulk coordination number is 8, surface coordination for the 100 surface is 4. So understand 100, that means the in the y and z axis it is not cutting, only the x is cutting, so it is cutting x, but it is parallel to y and z axis. Okay. So if you have x, y, z, so it is parallel to the y and z, so this particular plane could be 100, it is cutting the x axis, but it is not cutting the y and z axis. Okay. Crystallographic defects, crystals as we said forms uniform, but there are always chances of defects, because as the crystal keeps forming and forming, mixing takes place and the atoms come closer to each other and the crystal starts growing, so there could be defects. There are something called point defect, plane defect, and so on actually. So what is this point defect? That is, it happens at one single lattice point. Okay. So these are called vacancy defect. Instead of having one atom there, there is no atom, there is a gap, so that is called vacancy defect. Of course when you have like this, the structural strength goes down. Interstitial defect, that means atoms are occupying instead of being regular in their place where they have to be, they are in some odd place where it should not be there, that is called the interstitial defect. Okay. So point defect, you can also have impurities there. Okay. There is an impurity atom, because crystals, although they are supposed to be extremely pure with the 100% purity, sometimes an impurity like carbon can go and sit there. Okay. So the radius could be substantially smaller of that impurity or almost the same. Okay. Then there is something called anti-side defect. Suppose you have an ordered alloy of 2 different atoms, so they are placed like this, okay, one after another like this, but there is a rearrangement. Okay. Look at this, look at this. So instead of this being there and this being there, that is atom 1 and atom 2, they get interchanged. This is called anti-side defects. Line defects, they are called dislocations, that means some of the atoms are misaligned. Instead of suppose they are to be uniformly in a straight line, they are misaligned. So they called misalignment can be in a linear fashion, or there could be it could be in a curved fashion. Linear fashion we call it edge dislocation, that is termination of a plane of atoms in the middle of the crystal, or screw dislocation, that means helical path is traced around the linear defect. So instead of being a line, it could be twisted, so we call it screw defect. screw dislocation, that is called a line defect. Planar defect, grain boundaries occur where the crystallographic direction of the lattice abruptly changes, that is called the planar defect. Instead of line, the entire plane is defective. Okay. Now look at this. So in metals you can have individual crystals like this, so they are all forming. So but then there could be another crystals all forming, and each crystal is growing, and then finally they end up like this. These are called grain boundaries. So this particular crystal is grown, this particular crystal has grown, they all grow from different directions and they all hit, and this is called the grain boundary. So these grain boundaries are a little bit weak, and there is a lot of mechanical engineering studies talked about, so we will not go into this. But if you take a crystal and look under a very high resolution microscope, we can see these grain boundaries, okay, where defects, where the strength could be much lesser, there could be movement and so on actually. Because as the crystal starts growing from different directions, inside the crystal they may be uniform, but as they hit another growing crystal, another growing crystal, another growing crystal, they form this type of grain boundaries. Okay. These are individual crystals, the whole thing is a grain, and each grain hits each other during their growth, and they form the grain boundary. Now this is called the edge dislocation, where as you can see here there is a shift in their edges. Okay. Then you have the bulk defects. These are all 3-dimensional macroscopic defects such as pores. There could be small holes, there could be cracks, there could be some inclusion bodies, voids where there are no atoms, okay, cluster of vacancies. Okay. Impurities can cluster together, there could be some impurities, they all may come together, so there could be patches of impurities. So all these are also possible in a crystalline system. Okay. So impurities you can have, they can be filling up these voids, and if they are smaller or just equal, okay, then they are okay, but if they are very big, they may completely dislocate, the equilibrium position can be shifted away from their lattice side. So the impurities can be small like this, or just equal, touching each other, touching all the other atoms, whereas when they become very big, they are going to completely disrupt the crystal structure. Okay. So if let us look at this, suppose we have a small atom for a coordination number 6. So we have 4 atoms here of radius capital R and 2, one on the top, one on the bottom. So we have this small r which just touches all of these 4, as well as one at the top and one at the bottom. We can get some relationship between these small r and the capital R. Okay. These are all from geometry. So if I draw this radius, that is r plus r, and if I draw a perpendicular line to the capital R, this angle is 45 degrees, right. So cos 45, as all of us know, is 1 by square root of 2, which is equal to this small r divided by r plus r. This is from our geometry, we must have studied in our 10th standard. Okay. So cos 45, which is 1 by square root of 2, r divided by r plus r. So if I rearrange this, square root of 2r is equal to r plus r, then I divide by capital R, I will end up with r by r is equal to square root of 2 minus 1, square root of 2 is 1.414 minus 1 is 0.414. So ratio of the radius, this small r by capital R, is 0.414. That means I can fit exactly a smaller circle or a smaller, okay, which will have a radius equal to 0.414 of the bigger radius. Okay. If I have smaller, then of course this smaller circle will not touch all of them. If I have a bigger, it is going to dislocate or shift all of these things. Okay. So you have to keep that in mind. Similarly, if we want to look at 3 okay, where this is touching 3 of them. Again it goes through your geometry, okay. So how do we go do that? First we draw a big circle which will cover all these 3 small circle, okay. So we have a big circle which will cover, and then what will be the length of this particular perpendicular? Again it comes from your geometry, because this is an equilateral triangle. This radius is r, this radius is capital R, capital R, capital R, capital R, capital R, okay. So the length, this is called the median, the length of the median of this triangle. Suppose this equilateral triangle is r plus r, that is 2, length of the median of the triangle is square root of 3 divided by 2 into a. Again you have studied in your school, square median of an equilateral triangle, square root of 3 by 2 into the side is 2, because this is 1, this is 1. So that will give the square root of 3, that is this median. The radius of this bigger circle is equal to, okay, radius of the bigger circle is equal to this length plus this length, okay. This length is 1. Now what is this length? 66% or 2/3 of this median, 2/3 of square root of 3 plus this one. Do you understand? So what is the radius of this bigger circle? It is made up of this length plus this radius. This radius we will call it 1. Now this radius, that is the 2/3 of the median of this triangle, okay. Median is square root of 3, so 2 by 3 into square root of 3. Now once I know the radius of bigger circle, radius of this smaller circle is radius of bigger circle, okay, radius of bigger circle minus this, that will give you the radius of this. So radius of bigger circle minus this is 1 plus 1, 2, that is the diameter of this circle. So radius of bigger circle is given by 2 by 3 into square root of 3 minus 1, okay. So because this plus 1 and this minus 2 goes to minus 1, so it is 0.155. So the radius of this small circle which is touching all these divided by the radius of this bigger circle will have ratio of 0.155. So this is obtained of course from geometry, okay. So it is not very difficult. So I can have a small circle, it can be placed inside which touches all these bigger circle, and that size of that circle will be related with the size of the bigger circle by r is equal to 0.55, whereas in this particular situation we saw r by r is equal to 0.414 and so on. So we can do a lot of these type of calculations, okay. So for coordination number 3, r by r, that is radius of black to white 0.155, coordination number 4, that is the tetrahedron, radius of r by r 0.225, coordination number 6 0.414, that is HCP, coordination number 8 r by r is 0.732, coordination number 12 r by r is 1. So this tells you the central atom radius as against the bigger atom radius, this is the number it should be. If it is bigger, it is going to disrupt the lattice, okay. That is so based on these numbers one can even think about what type of impurities to add to the existing metal, okay. There is something also called the atomic packing factor, okay. So we will talk about this atomic packing factor in the next class, okay. Thank you very much for your time.